Alright, okay, this video is following up with the previous video on static equilibrium. So having understood how you should handle static forces, okay, use the balance of forces equations, we proceed to look at one of the questions in the tutorial. Okay, I believe by showing you the entire process, I will be able to integrate how your understanding of static equilibrium can be applied to the question. Alright, so the tutorial question we're looking at is a 6.9, okay, which is here. Okay, this is basically a beam, okay, having a uniformly distributed load over here and 2 point loads, okay, at B and E. Your supports are at A and D. Okay, so the typical flow is that you will need to draw out free body diagram, followed by a shear force diagram, followed by bending moment diagram. Okay, and I will show you the steps of exactly how to draw and how to derive the values of each of the important points. Okay, so free body diagram first. There is usually a scale that you should be using. Okay, so for this case, the scale is indicated here, okay, in the question, 1 cm for 1 meter, etc. All right, so let's do the FBD first. Okay, so this would be A, B, C, D. Okay, and this is E. So E has a 30 kilonewton. Okay, A is the support, right? So you should have a reaction here. Okay, reaction from the support. So I call this RA. Okay, at B, there is a 10 kilonewton. At D, there is also a support, so we call this RD. Okay, so this is 2 meter, 2 meter, 4 meter, 2 meter. And your UDL okay, so this is your free body diagram, right? Now then we proceed on to the shear force diagram. Okay, we are going to draw down, okay, the appropriate lines, the key points over here. So this would be X, okay, distance along the beam. The y-axis will be your shear force, okay, which is Newton, kilonewton. Okay, and this is your shear force diagram. Okay. Okay, what is the convention for shear force? It is actually given in the lecture notes. All right. If there is a force that makes the left side of the beam tends to go up, okay, then the shear force is positive. Okay, if it tends to make the left side of the beam tend to go down, right, then it is negative shear force. Okay, so for this case, we are going to start from left and proceed to the right side, and we will look at how each of these forces and the UDLs will affect the shear force. Okay, first point, at A, Okay, the first force that it encounters is an upward force, correct? So it will go up. Okay, it will go up, and because that is the only force that it encounters, it is going to be constant, okay, throughout until it reaches B. Okay, then it will be pushed down by this 10 kilonewton. All right, and then it will end at somewhere lah. It will end at somewhere being go down by 10 kilonewton, and it will continue to remain constant until you reach C, where it starts to encounter a constant but proportional loading across the 4 meters. So the shear force is going to have a sloping downwards kind of line. All right, until it reaches D, it will face an upward reaction, so it will go up, okay, by this much. Okay, and then by the time it reaches E, right, it will be pushed down, and one thing for sure, it will always end up in 0. Okay, this one will start with 0 and then you go up. So this case is true, the 0, 0 is true when both sides, both ends are either simply supported or at the free end. Okay, it will not be true if it is at a cantilever side lah. Anyway, yeah, so for this case, it will start at 0 and at 0. Okay, but first of all, let's find the unknowns, and these unknowns are the RA and RD. Okay, I'm going to leave this space over here to draw the remaining diagrams, so I will use a separate sheet. So what are the equations that we can write? Okay, the first one is sum of forces in the y direction, which is the vertical direction, equals to 0. Okay, then you are going to define yourself. Okay, one direction is going to be positive, so the other direction will have to be negative. Okay, so if we take upward as positive, then RA and RD will be positive. Okay, and the others are all negative in this equation. So what we should write is RA plus RD minus 10 minus 30. Okay, and for UDL, right, when you have 20 kilonewton acting for every meter, so what is the total force? 20 times 4. Okay, and they are all acting downwards, so this will be your equation. Okay, so RA plus RD equals to minus 20 minus 30 minus 80, so it's 120 over here. Okay, this is equation 1. Next, I will take moments about a certain point, okay, equals to 0. Like what I mentioned previously, if the whole system is in equilibrium, no matter where you take the moments about, the sum of moments will always be 0. Okay, so for convenience sake, because if I take moment about A, the moment caused by reaction A will not be there, so I can directly solve for D. Okay, so I can take moment about A equals to 0. Okay, and what happens to this now? We look at every force, and then we ask what are the moments caused by these forces about the point A. Okay, and also we have to define ourselves. Do we want to take clockwise as positive or anti-clockwise as positive? Okay, if I take clockwise as positive, then the anti-clockwise moments will be negative. Okay, so for this case, we will have positive, positive, negative, positive. Okay, because the force at B is doing this motion, the UDL will cause this moment also. Okay, but RD will be anti-clockwise, so RD will be negative. Okay, so 30 kilonewton also clockwise. All right, so okay, by B it will be 10 kilonewton multiplied by the moment arm, the distance from A, perpendicular distance, which is 2. Okay. The moment caused by E, okay, is also positive, so 30 times, what is the moment distance? The whole length, okay, which is 10. Okay. What about the moment caused by the UDL? Okay, the moment caused by UDL can be represented by one single big force, okay, which for this case is 80 lah, because 20 times 80 ma. The moment caused by one single big force acting at the center of the UDL. Okay, so for this case, you imagine a total grand force of 80, okay, acting at this 2 meter distance, this midpoint over here. Okay, so acting at here, and this is also causing clockwise, right? So it should be positive, plus 80. So what is the distance? The moment distance is this distance, okay, 2 plus 2 plus 2, okay, so times 6. All right. And finally, so this one done, this one done, this one is taken care of by representing it as a single force acting in the middle. Now we're left with RD, which is anti-clockwise, and it should be negative. Okay, negative RD times, what is the moment distance, moment arm? 224, 8 meters. Okay, equals to 0. Okay, so here you can solve lah, and eventually you will get RD is equals to 100 kilonewton. All right, and we can go back to equation 1. Okay, RA plus 100 equals to 120. So RA would be 20 kilonewton. Okay. So now let's update our free body diagram. So now you know this is 20. Okay, RD is 100, right? So so now we can draw the SFD, the shear force diagram. Okay. Okay, first force being pushed up, so it's a positive shear. Okay, by 20. You should go to scale, okay, to draw this height. You should follow to scale. But for my case, 20. I'm just going to do rough. Oh, I'm also going to do to scale but just my scale So start from 0, it will go up, push up by 20. So this is 20. Okay, then it's going to stay constant at 20. Okay, and by the time you reach B, it's going to push down by 10. So 20 push down by 10, my new location will be 10. Okay, 10, and it will be constant again, constant until I reach C. Okay, so here is still at 10 kilonewton. Okay, from C to D, I'm going to gradually get pushed down slowly. Okay, gradually push down more and more. For every meter I travel to the right side, okay, I will get pushed down by 20, 20, 20, 20, until I push down by a grand total of 4 times 20, which is 80. Okay, so from 10 I get pushed down by 80 until when I reach D. Okay, I'm pushing down by 20. So from 10 minus 80, my new point would be minus 70. Okay, so this is the new point. Okay, UDL will produce this kind of shear force. Okay, and this new point is minus 70. Okay, when I reach D, I will get pushed up by 100. Okay, so from minus 70 I push up by 100, so I will go up to plus 30. Okay, so this is 30. Okay, and I'll remain constant 30 until I reach the end, where I eventually push down by 30. So I will go down by 30, so it will end up at 0. Okay, like I say, it will start at 0 and end at 0. Okay, this is only true if your beam is simply supported end or free end. Okay, so we have cleared one shear force diagram. Okay, so I'm just drawing the line further down to draw the bending moment diagram. Okay, but before that, because of this UDL, okay, which causes this shear force, it inherently creates an extra point that we have to pay attention. Okay, and it is this point. Okay, this point here, because this point the shear force intersects at 0. Okay, so we have to find out what is the distance that intersects. Okay, so for this case, right, this is the length that we have to know, that we have to find. Okay, and we can call this value x. Okay, in fact we can mark this location as x. Okay, how do you find this distance x here? Okay, you look at based on the video, the online video, you're supposed to use the way there is similar triangles. Okay, means you compare two triangles, the length of the two triangles, they should be similar. Then you will be able to find how much is this. Okay, and the two triangles is basically the two that is created from this shear force. Okay, so the first one is this small triangle. Okay, the second one is this large triangle. Okay, and you say the small triangle is similar to the large triangle, which means the height is, the ratio of the height will be the same as the ratio of the base, will be the same as the ratio of the hypotenuse. Okay, to put it simply, if I have a triangle like this, I have a triangle like this. Okay, this is A, B, C. Okay, and this is small a, small b, small c. Then similar triangle says that A over A equals to B over B equals to C over C. Okay, that's what means by the similar triangles. So how do we find x using this method? Let me see. I am going to compare the base, okay, with the height. So the ratio of the small triangle to the large triangle, so the height, okay, so let's use capital letter for big triangle, small letter for small. So the height is height over height equals to base over base. Okay, height is this one, okay, and base is this one. Okay, so the small height, what is the height? It's 10, right? It's 10. The big height is the actual magnitude itself. The magnitude is 70. Okay, so equals to, what is the small base? It is x. Okay, the distance is x. What is the large base? Okay, this whole thing is 4, right? So this should be 4. The large base should be 4 minus x. Okay, so then we do cross multiplication. Okay, 40 minus 10x is equals to 70x. Okay, so 40 is equals to 80x. X is equals to half. Okay, so we managed to find the zero shear force. But this is not the answer because you have to follow the question. Okay, the question is determine the position of the zero shear force from A. So this is the answer, not this one. This one is 0.5, but what is this one? Okay, so the answer, right, is 4.5 meter from A. Okay, you have to add this 4 meter because it's with reference from A. Okay. Okay, so we are truly done with the shear force. Next, we move over to bending moment. Okay. Bending moment is more challenging. Okay, but with the knowledge that you managed to get from the static equilibrium video, you should be able to have a rough understanding how to approach. Okay. So we are going to draw the bending moment diagram over here. All right. Then we look at the question. Then we look at the shear force. So this is bending moment. So this is how you draw the bending moment diagram. You look at the shear force. Okay. The gradient of the bending moment line is the value of the shear force. Okay, again, the gradient of the bending moment line which you're going to draw is the value of the shear force over here. So take for example, between A to B, okay, from A to B, the shear force is a constant value of 20. Okay, this means that the bending moment between A to B will have a constant gradient of 20. Okay, so it will have a positive 20 gradient. Okay, so it is a line going straight up. Okay, then there's one more thing that you also need to know. Bending moment, okay, at simply supported points and also at free ends are zero. Okay, because they are free to rotate, so there's no resisting moment. The bending moment at both ends are zero. So very similar to shear force, it's going to start at 0 and end at 0. Okay, but cantilever, again, cantilever, it doesn't apply. Cantilever, because you are restricting the base. So for the ruler itself, it will feel that there is a bending moment at the base, so it cannot be 0. Okay, it's not like a simply supported or free end. It's free to rotate, so the bending moment is 0. Okay. Okay, so it's going to look like this. It's going to have a slope of 20. Okay. So let's say the gradient of this line is 20. And B to C, the shear force actually dropped down to 10. So in this case, the slope of this straight line from B to C is going to be less steep. Okay, because the slope will drop from 20 to 10. So you're going to have a straight line sloping upwards but less steep, because the gradient here is going to be 10. Alright, so that's how you need to interpret. Okay, then you're going to ask me, so what is the value of this at this point here? Okay, what is this value? Okay, and also what is this value? Okay, straight and simple answer. You see, if my slope is 20 here, right? So it means for every meter I move from left to right, for every meter I progress, I will increase by 20. So by the time I hit B, which is, this is 2 meter, right? By the time I hit B, I will have 20 and 20. So this bending moment is 40. Okay? And you go to B and C, B to C, these 2 points. This distance is also 2 meters. But this time, I will increase by a slower rate. I will increase by 10. Okay? So 1 meter, I increase by 10. Another meter, I increase by another 10. So this value here will be 60. Okay? And the units for BMD, of course, is kilonewton meters. Okay? Because you are multiplying kilonewton force times the distance. So it's kilonewton meter. Okay? Let's not talk about the central part first. Let's look at the end part. Okay? The end part. Here, this part, D to E. Okay, this is also 2 meters in length, the beam. Okay, and you know that the gradient of this line is going to be a constant value of 30. Okay, I am going to have a straight line here, constant value 30, positive plus 30, so it's sloping upwards. Okay, and you also know that it's going to end up in 0 here. Okay, because start from 0 and at 0. So for a line to be climbing steadily at a gradient of 30 until it reaches 0, I will have to be like that, right? Okay, 30, 20. So it should even be steeper than the first line. So it should be around this. Okay, sloping up, gradient 30 and at 0. Okay, that's the scenario. Okay, so what is this value here? Again, it is 2 meters, and it is climbing 30 for every 1 meter, right? So I should start from minus 60 over here. Okay, minus 60. After 1 meter, I reach minus 30. After 1 meter, I reach 0. Okay, so we are done with the constant gradient portion. Just remember, when there is a point load, it gives you constant shear force, which gives you straight lines for the bending moment. Okay, but when there is a UDL, it gives you a sloping line in the shear force, and this sloping line, right, will give you a curve in the bending moment. So now we're going to learn how to draw the curve. Okay. Like I said, the value of the shear force is the gradient of the bending moment. So this portion, this is what's going to happen. Okay, let's split into 2 portions. The positive shear force portion and the negative shear force portion. Okay, for the positive shear force, okay, you know the line here, bending moment is going to keep on climbing up. Okay, but you will climb until it reaches 0 gradient. Okay, so it's going to climb up until it reaches 0. So this is actually a curve over here. Okay, this is a curve over here, and you will hit 0. 0 gradient means it's a peak. It will peak over here. Okay, now let's look at the negative shear side. The value is going to increase more and more, right? I mean, we get more and more negative. So it means it is going to be a curve here, and it's going to get steeper and steeper, sloping down, more and more sloping downwards until it reaches this point. Okay, until it reaches this point. Okay, so how does it look like? It's going to, again, this one is from the peak, right? So it's going to gradually get more and more steeper downwards, sloping downwards. Okay, so this is how it's going to look like. Okay, front portion climb up slower and slower until it reaches the peak, and then back portion drop down more and more steep until you reach this point. Okay. So now we have a few key points to find again. What is the peak over here? Okay, first we have to find what is the peak. What is the value here? Okay. Second, what is the point of intersection here? Okay, this is called the point of contraflexure. Okay, where your bending moment starts to turn from positive to negative. Okay, so this is the point of contraflexure. Okay, so again, this is an important point. I'm going to draw something like this. Okay, and let's call this distance. Let's call this distance. Okay, this small distance here, y. Okay, small y. Okay, and in fact, I'll call this point, contraflexure point, capital Y. Okay. Okay. Okay, let's first solve this point first. What is the highest point over here? What is the highest point over here? Remember I say back in the static equilibrium video that wherever you cut, right, when this whole system is in equilibrium, if you cut a section out, right, any section, they will also be in equilibrium. Okay, so that's what we're going to do. So since we are looking at this point, right, we will cut at this point. Okay, cut at this point, and what do? We will draw the free body diagram of the left hand side. Okay, this point is x, right? So let's cut at x. Okay, so you're gonna have this free body diagram. This is A, which is 20. Okay, at B, you are going to have 10. Okay, this is 2 meters. At C, this is 20. Okay, this is C, 2 meters, and you know X is 0.5 meter. Okay, this one you found just now, right? Okay. When you cut as a beam at somewhere, right, it is going to reveal an unknown force, unknown shear force. Let's call this Fx. Okay, and it is going to reveal an unknown moment. Okay, moment. The next step we're going to do is we need to find M. So how do we do it? We sum our moments about the point where we cut x. We sum moments about x, and it will be equals to 0 because the system itself is in equilibrium. Okay, so let's do this. So I take moment about x. Okay, let's say anti-clockwise is positive now. Okay, let's call the anti-clockwise to be positive. So we're going to have positive, 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 and this is the only negative moment. Okay, because it's going clockwise about x. Okay, so first one is M. It's going to be positive. Okay, let's look at the 10 kilonewton plus 10 times what is the moment arm? 2.5. Okay, times 2.5. Okay, and positive moment caused by the UDL. Okay, again, to find a moment, it can be represented by one single force acting at the center of the UDL. Okay, so what is the total force over here? Total force by UDL. What is it? The length multiplied by the 20. Okay, this is because this is 20 kilonewton per meter. 0.5 times 20. So this is 10. Okay. Acting at the center. Okay, center is over here. Since this is 0.5, right? So the center will be 0.25. Okay, so it is 10 times 0.25. Okay. So you're actually representing UDL by a single big force acting at the center of the UDL. Okay. I hope you understand this. 1, 2, 3. Done. Now we are left with this one. So this is minus, because it's clockwise. Minus 20 times the moment arm total is 2.5, 4.5. Okay. So this whole thing is equals to 0. Okay. So from here you can find M. Which will give you 62.5 kilonewton meters. Okay. So the maximum point here, this one is 62.5. Okay. So from 60, it only climb up by 2.5 to hit the maximum. Then it starts to decrease already. All right. Okay, so last part, we want to know the point of contraflexion. Okay, how do we find this one? Again, the approach is the same. You cut the beam at this point at Y. Okay, you cut the beam at Y over here, and then you draw the free body diagram. Okay, I'm going to show you. Okay, then your question, one of your question will be, sir, if I cut, must I look at the left hand side? The answer is no. Okay. You can also look at the right hand side. When the forces are much simpler on the other side, the recommendation is to use the side with less forces. Okay, so let us cut at Y, because since there's only these few forces, and we will balance out the forces and moments. Okay, so for this case, your free body diagram will look like this. Okay, this is E. I have a 30 downward. Okay, D is 100 upwards. Okay, this is 2 meters. Okay, and this is Y. Okay, the point where we cut is Y. This distance is Y meters. Okay, and your UDL is 20 per meter. Okay, E, D. Okay, this is your free body diagram. So when you cut again, it will reveal a shear force here. Okay, let's call this Fy. It will also reveal a moment over here. Okay, we call this M. Okay, your next question will then be, sir, why did you draw, when you cut, look at the left, your moment is anti-clockwise, but when you cut, look at the right, your moment is clockwise. Okay, my simple guidance would be, the beam that you look at, right, when you draw the moment, make sure the moment is making the beam smile. Okay, for this case, when you look at the left hand side, the moment that you draw is anti-clockwise, right? Because the moment here, when you draw anti-clockwise, it will make the beam smile. Okay, if I draw clockwise, the beam will frown. Okay, so this is the simple guideline. Okay, so for your case, for this case, I cut the beam, I look at the right hand side of the beam. The moment here, I should draw and make the beam smile. Okay, so drawing it in the clockwise direction will make the beam smile. Okay, that is the guideline for me. Alright, finally, we are going to sum the moments about where we cut, which is y, equals to 0. Okay, so let's take clockwise to be positive and anti-clockwise to be negative. So this one will be positive. UDL will give a positive moment. The force at E will give a positive moment. Okay, only the force at D, the 100 kilonewton, will be anti-clockwise. So this is a negative moment. All right, so let's go. Positive. Okay, let's look at E first. Positive plus 30. What is the moment arm, the distance? 2 plus y. Okay, times 2 plus y. Okay, plus UDL. What is the UDL cause? What moment does it cause? Again, you represent it by one single force acting in the middle of the UDL. Okay, acting here. Okay, so what is the force and what is the moment arm? The force is a total of 20 multiplied by y meters. Okay, 20 times y. The moment arm is halfway across, right? So it should be half y. Okay, so 1, 2, 3. And then finally, the anti-clockwise will be negative. So minus 100. What is the moment arm? Y. Okay, times y equals to 0. This is your equation. Okay. So from here, you can see that there are actually two unknowns, right? One, y is an unknown. The second one is m. So how to solve? M and y, two unknown, one equation. Well, if you look at your bending moment diagram, at the point y, right, what is the value of the moment? Is 0. Okay, so basically your moment m is 0. Okay, so m is equals to 0. Okay, so you are left with an equation with only one unknown, which is y. Okay, so just solve it. 60 plus 30y plus this one will give you 10y squared. Okay, this one is minus 100y. You're going to end up with a quadratic equation. Okay, 10y squared minus 70y plus 60 equals to 0. Okay, and you're going to have y is equals to 6 or 1. Okay, so which one do you think is the correct answer? When you look at this, you see the y is actually some distance within the 4 meters. Okay, so y could be somewhere around here. So if you tell me y is equal to 6, is over the UDL already, so it's not correct. Okay, so 6 is rejected. Okay, so the answer is y equals to 1 meter. This is the point of contraflexion. Again, he's asking for point of contraflexion from D. So this is correct. Okay, so it is 1 meter from D. Okay, so this is the full flow of the SFBM long question. Okay, all the aspects, the important aspects, I've gone through with you, and how to solve, how to find the bending moment, how to find the shear force, how to find the zero shear, how to find the point of contraflexion. Okay, if you have any questions, just feel free to ask me.